All right, I hit the record button, which is something I'll probably have to have help getting reminders to do because we're going to have a lot of people hopefully joining in. But if anything comes up, I don't want to have people not able to follow what we're doing in class.
Have that printer selected.
So maybe we'll talk first about Zoom etiquette. Everyone go ahead and mute your screens, which is in the bottom left corner if you're not talking. That just helps so the background noise, you can have parents talking to you, you can have babies crying, you can have thunder outside, whatever it is, and it doesn't interfere with the conversation. I do love it if you're all willing to show your faces. It just feels more like a class and a conversation. If for some reason you can't or you don't want to, feel free to mute your video or pause your video, stop video, I think it says in the bottom left corner. That's an option that you have as well. I do have the option to mute someone. So if someone just is unaware that they're unmuted, I can mute you. And then when you start talking, usually it comes up with a little bar across your screen saying you're muted. In case you want to unmute yourself, you might want to do that. So it sometimes registers that you have loud noise in your place and maybe you're trying to talk. The other way we can get people to talk is there's a chat button. If you haven't used Zoom a lot, at the very bottom of your screen, if you move your cursor around, there's a little chat at the bottom. And if you click that, it kind of expands out a chat. And so you can send a message. So I can say, hi, everyone, and I can send it to everyone. Or you can send it, if you click on the everyone that's in blue, you can send it to a specific participant. The other thing that we can do is if you click on the participants button at the bottom, there should be an option to say yes, no, go faster, go slower, thumbs up, thumbs down. And I thought there was a hand raise option, but I don't see that. So there's an option to kind of give some feedback that way. What I'm going to ask is that if you have a question you'd like to ask, probably just try unmuting and saying something, because if I'm drawing, I have two monitors and I'm going to be drawing on the screen over here. So I might not see the chat window or the yes, no, hand raise kind of stuff right away. Anyone have questions on how we're using Zoom? Questions? Okay. Let's go ahead and jump into class then. And what I'm going to do is I'm going to start by sharing my screen. And I believe that if someone has a question about something on the screen and it's not easy to verbalize, I think you can annotate my screen. So if we get to that point, we'll go for it. So I'm going to share the screen over here. We'll go full screen. And I believe now you should all be able to see my screen. Tina, I can see you at the top of my screen. Can you confirm that you can see my screen?
Yes, I can see it.
Fantastic. Thank you, Tina.
Sure.
Okay, we're going to go ahead and do our first clicker question of the night. We're going to do this as a numeric answer. Okay, this should be sent out to your clickers as well. And what we're going to be doing is I'm going to send everyone into breakout rooms. What that means is you're going to be in a group with a few other individuals, and I want you to have conversations. I'm going to send the learning assistants and myself into those rooms as well. So let's do 4 rooms, and we're going to move participants to breakout rooms automatically. Breakout rooms close after open all rooms. And I think this might be harder than I thought. So on your own, try to figure out how to work through this problem. And by the way, if you have not already seen the announcement, there is a worksheet that I emailed out to everyone. It's a link in the Blackboard announcement I sent an email, but it's also under Blackboard content. And you should be able to get that there. That'll just save you some time so you don't have to write down the questions, either if you want to print that out or if you want to have it virtually, if you can write on it with a tablet or something like that, that'd be fantastic.
I can't hear a thing.
Alexandria, can you hear me?
Okay, yes, sorry. I'm on my phone now. I was trying to get on through my laptop. For some reason, it's not loading. So I hopped on my phone.
It's okay. So if you are on your phone with video, if you want to join to show your face, most people are. If you don't want to, it's okay. But everyone's in breakout groups right now doing the first clicker question, which you probably can see on your iClicker app. So if you want to join, you can kind of look through that. I think I'm about to pull everyone back in. Otherwise, I would send you into a group. So
Okay.
just go ahead and make sure your iClicker app is pulled up and then decide if you want to be on video or not, like most people are. And then we'll kind of figure it out, all right?
Okay, thank you.
And I'm going to figure out how do I do in breakout rooms. I guess I just close them all.
I think maybe. I don't know.
Here we come. Oh, 60 seconds. That makes sense.
Okay, I'm gonna go grab my notebook. I was struggling. They sent me this modem for class, and I tried to hook it up in my port, and for some reason, there's nothing to hook it up to. And my mobile hotspot on my phone isn't working. It's just a mess.
I'm glad you're able to get on this way. That's going to be pretty decent as long as you have some video to see what we're doing. So it looks like
Okay.
everything went back into the breakout room or to the main room. So
How do I go there?
you are there. I didn't send you into breakout room. So do you have video right now?
I could try to put it on. I can see you and with this backdrop behind you.
Yeah, and if you click on in the top right corner, there's speaker view, and then there's a little gallery panel, which is all the little dots. I think you should be able to see everybody in there.
Okay, let's see.
So we have 17 responses.
Let me try to. I'm gonna mute myself so I'm not talking the whole time.
Sounds good. So I think we got a big audience now. We have about 20 some people.
Oh, okay.
All right. How we doing? So I saw, popped in a couple of different rooms and I saw some discussions being had, and the discussions revolved around whether we take the negative log of the Ka value, negative log of the concentration, or if we have to do an ice table. Can I get someone to volunteer maybe to describe which one your group chose and why? Go ahead and unmute yourself, and the first person to talk is in. Or we can randomly pick.
Got to do the ice table, Dr. Bailey.
Why is that, Jesse?
Because acetic acid is not a strong acid, so it's not going to totally dissociate.
All right, so that's one of the things that we're going to have to keep in mind now. Is going forward, we need to be able to distinguish between strong acids and weak acids. And today's class hopefully is going to get us on the same page about what all those things are and how to differentiate between them. So hopefully everyone can see my screen again. And we're going to talk about how to do this. So in the end, let's see. Can we see the writing on the screen? Lauren, can you give me a thumbs up if you can see some scribbling on the screen? Sweet. Okay. Just wanted to make sure. If we're asked to find the pH, in the end, we're going to want to find negative log of the concentration of H+ ions at equilibrium. And the most common mistake that students will make is they'll say, oh, this is an acid, so we'll just do negative log of 1.25 molar. But that assumes that all of the acetic acid reacts and becomes the product that we're going to be talking about today, which is acids. So we need to think about what is going to happen with an acid. I'm trying to remember in Miss Khatum's class right before last time you all were together, did she help define what an acid was? Lauren, do you know, are you able to define an acid?
An acid would be something that it's a hydronium donor, right?
Kind of getting there. So an acid, the definition we're going to use is called a Bronsted-Lowry. There's a couple different definitions. So that's why we're going to use this one called Bronsted-Lowry. It means it is something that gives up an H+ ion. It's not a hydrogen, because a hydrogen has an electron. I don't know why I can't write, but so hydrogen atom has an electron. An H+ ion, we call these proton or H+ ion, either one, they're interchangeable. So if a molecule gives away an H+ ion, that's considered an acid. If, on the other hand, a molecule accepts an H+ ion, that's considered a base. So in order to have an acid-base reaction, we can't have that without both of these. One of them gives up an H+ ion, one of them accepts that H+ ion. It's basically a transfer. It's like a bank transaction. You can't give away $100 unless there's someone accepting $100. So we'll keep that in mind. So the chemical reaction for an acid, this particular acid-base reaction of acetic acid, is here is our acid. Our H+ ion that's given away is this one here at the end. And that is given up to water. This aqueous means that it is also basically H3O plus, because that's H2O with an H+ ion. And then because it lost the H+ ion, now we have the same thing, but it has a negative charge because it gave up a positive H+ ion. All right. So if we have that, I'm going to go ahead and clear the screen. Our Ka value can be used just like any other K value. So a K value tells us what's at equilibrium, what's the concentration of products compared to the concentration of reactants. And every time we see a K value, that's really weird how I'm black, we're always going to write out or think about at least the expression concentration of the products over concentration of the reactants. And so that's what's written up here in the top corner. We're going to talk a little bit more about why for Ka, that's going to be a little bit different than Kc that we've done before, but for all intents and purposes, concentration of products over concentration of reactants raised to stoichiometric coefficient. So if we are assuming that in order to find the pH, we need to find the concentration of H plus at equilibrium, we know that that's not going to be 100% of it because our Ka value is relatively small. That means that we're going to have a lot more of the reactant than we're going to have of the product. So this number is going to be a lot less. This is going to be small, and this is going to be big at equilibrium. So if you haven't already written out your ICE table, I want you to go ahead and write out your ICE table and then figure out what your concentration of, or what your pH is and figure out the steps there. So I'll go ahead and give you about 2 more minutes to walk through that and then re-enter your clicker response. And I'm curious to see if those numbers change at all. I wonder if I can send you back in the same breakout rooms. Is that possible? Yes. I'm going to send you back in the breakout rooms so you can ask each other. Let's try to come back in 2 minutes. Welcome back. How are we doing? We got most people? It's hard to see. I think we got most people. All right. We have half the class in agreement and half the class not. So maybe let's start with what are the biggest challenges about filling in an ICE table? What are we going to put for our initial concentration of
0.
0.
what? Kat, were you one of the ones to answer that?
Yeah, sorry, my internet connection is bad. It's 0 moles because they haven't reacted. It hasn't reacted yet, changed yet.
Great. So we're assuming when we're talking about only initial starting concentration, One, because it's easier to calculate, but two, we're saying that it hasn't reacted yet, like Kat's saying, that we're going to put zeros in both of these boxes. The other challenging part, usually this part of the semester, is what do I put in the change? Do I put a plus x, minus x, 2x, 1x? What do I do? Who wants, Kat, do you want to keep going and say which one we do and why?
I think I've got this correct. The acetic acid is going to be minus X because it's going from 1.25 molar, the initial is 1.25 molar, so you know it's already been reacted and it's reacting to get the products. So those will be plus X. The H plus will be plus X and the CH3CO2 will be plus X.
So how do we know that it's minus on the left and plus on the right?
I'm assuming, this is an assumption, that if we already know the initial molarity of one of them, then it has already, I don't know, then the others haven't reacted yet. So it'll be minus instead. I don't know how to form that sentence.
Can someone help out?
Wouldn't it just be because we have products and reactants? So the reactants have to be used up and the products have to be created, and then the plus is the products being created and added to the solution?
So before equilibrium part of the semester, yes, the definition of a reactant is this used up. After that, the products are formed. This is no longer that part of the semester. So today it happens to be this way, and with almost all acid-base chemistry, it's going to be that way, that you start with zero products. But in this case here, because we put something into water, we have some of that, and we're saying we don't have any of the others. This reaction can only go one direction. You will not always have that. In the next couple of weeks, we're going to have stuff on both sides, and you're not going to be able to say, well, the reaction goes to the right because those are products. So we have to be really careful. So we have to have a better way. So what's a better description for why we're going to use up this reactant and form these products?
Got to get to equilibrium.
How do we know we're not at equilibrium, Jesse?
Because of the Ka value.
Be a little bit more specific.
I mean, it's not zero.
And
one. What?
you're so close. Can someone add in?
Was it just less than 1?
Ka is less than 1. That's true. But how do we know we're not there?
Because if you plugged in what you got right now, I mean, if you divide 0 by 1.25, you get 0. That's not what the Ka value
Great.
is.
So what Jesse's saying is if we found the Q value, it would not
okay.
be Ka.
Yeah.
Remember that whole part of the semester we talked about like 2 weeks ago? No, it was a long time ago, 3 weeks ago maybe, where we said we have to find the Q value. If Q is equal to K, then we don't go forwards or backwards, we're done. So that's exactly what I want us using here. So all those foundational things we talked about with what K expression means, right? Concentration of products over reactants at equilibrium. What is Q? How do we get from Q to K? We're always going to move from Q to K, whether that's forwards, backwards, whatever that is. So we can say, well, there are no products now. At equilibrium, this is not 0. So that means we have some of each reactants and products. So we have to use some of this reactant and make some products. Okay. So then what's our equilibrium concentration? We start with 1.25, we get rid of X. And so now it's a little bit less than we started with. And then we make some of both of our products. So now the big question is, what is X? Like, if you were to say X is, so I'll start off, but I want to hear other people's description of what X can be described as. X is the equilibrium concentration of acetate. What are some other descriptions of what X can be? For instance, what does this X here represent?
The concentration of the H plus.
Almost, keep going.
Oh, at equilibrium?
Yes. So the concentration of H plus ions at equilibrium. What is this X here, this minus X? What does this X represent?
The change in concentration of acetic acid from where it is now to equilibrium.
Fantastic. And you can also say that this here is the amount that the acetic acid decreased in concentration to get to equilibrium. This one here is how much the concentration of H+ ions increased to reach the equilibrium concentration, and same here. Okay, so it's really important that we define what X is and not just go through a whole bunch of steps. So which one of these values is useful to answer our question that we have up here?
A hydrogen ion
Be more specific?
at the concentration of the hydrogen ion at equilibrium.
This X right here. Great. So all these other X's are going to be tied to it, but really the only one that we care about is finding this one. So we can take the negative log of that to find the pH. So are we comfortable with finding that value? So we set it up. Ka is the concentration of products. X at equilibrium. X is one of them. X is the other. So X times X is X squared over the concentration of our reactant at equilibrium. Can we do anything to simplify our lives?
It is a weak acid, so you can take away the minus X on the bottom.
What does that do if we take away this minus X?
It makes it easier to work the problem.
So because it's a weak acid, or Ka value is less than 1, we can say, well, we're going to assume that the initial concentration of our weak acid changes so little that we're going to call this about the same as we started with. And if that holds true, it does make our life a lot easier mathematically. So we can go ahead and solve for X squared. We can solve for X. And then how do we find the pH from this point, Tracy?
The negative log of X.
And if we do that, then we find a pH of 2.32. We done?
Yes.
Yes, we have done.
Okay, would we not round up, because I got 2.3279, so would that not be 2.33?
So if we actually put the values in and do all the calculations, I believe that if you do 4.7, yes, 4.7 times 10 to the negative third. But if we didn't round the entire way through, I think the answer is 2.32 if we round to the second digit. Can anyone else confirm that?
Yes, I plugged it in from my calculator, just kept using the same numbers, and I came out with 2.32.
Great. Great question, Kat. So when we're writing these things out, we never want to write them out and then just use them at the shortened version. We always want to keep it in our calculator and keep using that number until we have to report something out, and then we round it. And actually, this should probably be 3 sig figs, because this is 1, 2, 3 sig figs. This is a logarithmic number, so we should actually probably do 2.322. It should actually have one more number here, because in logarithmic values, right, we did a log of it. It's how many numbers are past the decimal is how many significant figures we have. So I messed up. So what did we forget to do though? What do we have to do that we forgot?
Check to make sure the percentage is less than 5%.
Absolutely. So we want to make sure we made this assumption up here that this change was really, really small. What if it was half of it went away? Then our assumption is not valid anymore. And that depends on this initial concentration in the Ka value. So we're just going to make the assumption every time. And then we're going to say, okay, well, how much was it actually? So we know it's 4.7 times 10 to the negative third is how much the change was. 1.25 molar is what we started with, multiplied by 100 to give us a percentage. And I get 0.3, what is it, 339 maybe, something like that. It's less than 1% of that initial value was disassociated in order to get to equilibrium. So assumption is valid. We're good. We don't have to do the quadratic. Any questions on that? Okay, that was a nice quick intro, right? Now we're 36 minutes into class and time to talk about our learning objectives. It's amazing how fast all this stuff goes. I'll stop that poll. All right, so by the end of class today, I want you to calculate pH given Ka or Kb. We're gonna talk about what Ka and Kb are and how they relate to each other. We're going to look at relative strength of acids and bases using Ka and Kb. And then we're gonna say how Ka and Kb relate to each other. And then we're gonna do some calculations with pH, pOH, concentration of H plus, and concentration of OH minus. I wanted to get your input though while I had everyone together. The input that I would like from you all is on workshop. We want our workshop leaders, our learning assistants, to use their time wisely. So I want you to look at these three options and see which one of these you think would be the best use of their time. I know that everyone has a lot of stuff going on now. Maybe some people have a lot more going on than they did before the COVID stuff happened. So I want to know whether you'd like to have supplemental workshops continue and have it be with a POGIL activity so that you're kind of all working on the same thing. That's option A. Option B is maybe ask them to hold tutoring sessions, which are not guided by POGIL activities. You come to them with homework problems, with stuff from class, whatever that is. Or the third option is just have them in class with us like they are today. So if you notice, Tripti and Josh and Diana are all with us today, along with Hemendra. And so we want this option to basically say, I don't think I have time to do a supplemental workshop throughout the week or tutoring. So I prefer that. So you go ahead and click in one of these three responses. That would be really useful for us to make a decision on how best to spend their time. Couple more seconds for everyone to get a response in. Very interesting. Okay, can you guys see that clicker poll? I don't know if it's visible to you all. Tracy, can you say your thumbs up or thumbs down? Can you see the poll results? Okay. So it looks like there are people that would keep taking advantage of it. Maybe I'll have to do, I hate doing another poll. I don't want to do another poll. I'll try to figure out, I'll send an announcement out about what I do with these results, because these results are, it sounds like there's use in keeping them available outside of class. So we will discuss that with them. Next question is about lab. So there's two options for lab. The night lab. I think that the day lab, I think there's a few of you in the day lab, and I don't know that these options are available during the day lab. But with Hemendra, we had talked about doing synchronous labs, which means that right after class, and this would start next week, not this week, because this week is supposed to be everyone together. Would you like for everyone to be working on a virtual lab together, to have Hemendra there? He's going to show you how things are done, and then he's going to be available for an hour and whatever afterwards to help you work through it. Or would you rather have that initial setup and then say the lab is due Wednesday at the end of lab? The question really relates to, with COVID stuff going on, is it now really difficult to participate in the night lab at the set times for the set amount of time? So the first option is regular times, have Hemendra there, and we might not need much of the time on Wednesday because some of the virtual labs are a bit shorter, so we might be able to get everything done on Monday night. The second one is he'll be there to help us set up right after class, and then you can work on your own and submit things by Wednesday. So go ahead and submit one of those two options if you have the night lab with Monday, Wednesday night with Hemendra. Maybe my wording of questions is not amazing.
Yeah, what does have between class on Monday mean?
So basically what I'm asking is, do you want to have time between, like, do you want to do it all Monday night with Hemendra there? Or do you want to just have him set you up and then you have the time between class Monday and Wednesday to complete the labs? So basically this option would be, I'd really like it not to be due until Wednesday, the top option is I'd rather complete it, have all of us complete it before we leave.
Okay.
Night, or whatever time that is. Does that help clarify?
Yes, thank you.
Okay, we have 13 responses. Any more people we're waiting on? I think the rest of the people during the day. Okay, people are leaning towards having the freedom, but okay, I'm gonna have a conversation with Hemendra then afterwards offline about potentially being available Monday night, but then not requiring it to be due Monday night, and having the people who have to leave that they can then come and do work on it on Tuesday or Wednesday and turn it in by class on Wednesday or something like that. All right, last question. This class is synchronous. All of us are together at the same time, responding to clickers and me having the chance to see what you guys are working on and working together. That is an option. I want to know what's going to work best for you. So synchronous is an option. If it is really, really difficult for you to do this, then I have the option to do basically, this is supposed to be asynchronous classes where I record on YouTube and I can insert questions. So you have to answer a question before you move forward. And then you can see, basically you have to try to solve it and then I'll solve it. And then we'll see how that works together. But that's not going to be feedback immediately. That's going to be more lecture based. So I want to know, would you rather keep it synchronous? Would you want it asynchronous, which is this option B that was not A in front of this, it's supposed to be asynchronous? Or would you like to have some asynchronous or some synchronous? And maybe I can. All right. It looks like the majority of classes actually prefers to do synchronous classes. They are all recorded. And so what that means is that if you are unable to come to the class, you can watch and kind of go through, although when we're in breakout rooms, you're going to miss that because I don't think it records the breakout rooms. So there's just going to be some dead time where you have to work on your own. So we'll continue forward with this synchronous mode, but if something comes up and changes drastically, please let me know over email. I mentioned this to Jesse right before our class started today. This is the part of the semester that has the most practice problems out of the entire semester in POGL. And these activities are basically like, what is an acid? What does it mean to be a weak acid or a weaker acid? What are conjugate acids and bases? And that's all these. So the first three really deal with the topics we're talking about tonight in class. How do we calculate pH? These log scales are really difficult to calculate. And so this gives you a lot of practice, which is activity 45. Activity 46 is a more advanced topic. And that's, why is it that this compound is a strong acid and this one's not, or this one's stronger than this one? And so this talks about the molecular information behind why that is. And then this one talks about conjugate acid base pairs, and it gets into buffers, which we'll be doing, I think, next week. So these are some really good practice problems for y'all. And if we do them in workshop, we will be doing some of those. So there was a request for workshop. So if I'll send an announcement out tonight after I talk to Tripti and Josh, but if we have one this week, it's probably going to be one of these first three activities. So I'll send that announcement out tonight, which one of those it'll be. Okay. So that first problem that we did with acetic acid, it was really making a lot of assumptions that we haven't talked through yet. So what I want to do is kind of talk through those. So if we have an acid or a reactant, let's just say that there's a reactant that has a hydrogen ion, this H, attached to an anion, this A, and we put it into water, we can write out equilibrium constant Kc. However, a lot of these acid-base reactions, they don't use Kc. They use a simplified Ka or Kb. And the difference between these two equations is that they remove water from the equation. And they do that because it allows us to focus on, if you're doing these reactions with an acid and water, you're going to have so much water that really the thing that's changing is not the concentration of water, even though it's a reactant. So you're gonna instead you're gonna focus on everything else but the water. So Ka is a way to describe a simplified version of the reaction, where you have your weak acid, it dissociates, and it forms H plus ions in water, which you can describe as H3O or H plus, and an anion that's released. So if we look at the specifics of our last problem, the generic was we had acetic acid plus water, which we didn't even write in that first reaction, right? You didn't even see H2O there. And then the hydrogen ion that was transferred, the H plus ion, is the one in purple. And we ended up generating acetate, the negative charge, and hydronium ions. So in this case, our purple H moved from our acid to our base. And when they did that, the acid, what started out as the acid, now if we say, if the things on the right were to go in the backwards direction, what would this compound act as if it were to go from the right side to the left side? Does it accept a proton or does it donate a proton going from right to left? Anyone want to volunteer?
Gonna accept a proton.
So what do we call that, an acid or a base?
It's a base.
So these two are called a conjugate acid-base pair. It's the same thing with and without an H plus ion. And then water ends up accepting a proton. So on the left side, it's a base. On the right side, it's an acid, because the right side going backwards, it acts as an acid. So the simplified version of this is our anion attached to a hydrogen ion plus water yields our anion by itself plus H plus, or we can say H3O plus. You're going to see this type of terminology a lot. And if it's confusing to you, I need you to ask a question now. The simplified version is that you have the acetate. In essence, acetic acid is H plus ion attached to acetate. So we simplify that by saying anion and an H. And the bond that breaks is that bond right there. Do you have any questions on an acid-base reaction and how the simplified form that's at the top represents that reaction? Crickets? Okay. It's hard when I can't see everyone's faces. So our Ka expression is kind of what we wrote out before. It's the concentration of H plus ions times the concentration of our conjugate base. All right, we said that the thing on the right is our conjugate base over the concentration of the initial of the weak acid itself. So as our Ka value gets bigger, the strength of the acid gets bigger, because that means that it generates more products. Stronger the acid is, the more H plus ions it generates in solution. This p-value that we talked about before, it's always doing the same thing. So if we do pH, pKa, pOH, any of that, it's a negative log of that thing. So pKa is no different, negative log of the Ka value. So if we look at all of these, which of these acids that we have here is the strongest acid? And I think that this is on your worksheet as well, if you got a chance to print that out.
Is it phenol?
Everyone go ahead and click in an answer, and then we'll kind of like, it's all good. We'll discuss which one and why we think that. All right, a couple more seconds. All right, we've got 23 responses. We're split 19 to 5. So would anyone like to discuss, someone that hasn't talked yet? Describe which one you chose and why. Sarah Ray, are you choosing to share with us?
Well, I was thinking it was phenol, but if it has an OH, isn't that a base?
So we got to be really careful. A lot of our biology classes have trained us to think that OH is always OH minus. So OH attached to a carbon is not the same thing as hydroxide. Hydroxide is a strong base, and that if there's, this has 3 lone pairs on it, it's very different from OH that's attached to a carbon. So you picked out this functional group, which is the OH on the phenol, which is great to look at, but that's not going to tell us whether it's an acid or a base. So we can look for structural features, COOH, that is always going to be an acid no matter what. It might be stronger or weaker, but what we want to look at here is our Ka values and use those, or the pKa, either one of those, to determine which one's the strongest acid of all of these. So which one, if we look at the Ka or the pKa values, which one of those is going to tell us that it's the strongest acid? And why?
Would it be the first one?
Why?
Because it has a larger pK. I mean, it has a larger Ka value and a smaller pKa value.
Okay.
Which means it's a stronger acid.
Yep. So we said over here that the bigger the Ka is, the stronger the acid is. And what I want you thinking about is, remember that any K value says, did I freeze? Can you guys hear me? Okay, sorry, it looked like it froze for a second. Any Ka value or K value says that it's a concentration of products over the concentration of reactants. A strong acid is one that releases a lot of H+ ions. So the bigger the Ka value is, the more H+ ions are released when it gets put in water. And that's what makes it a strong acid. We know that the negative log of a bigger number is a smaller number as well. So what you're going to start to notice with these Ka and pKa values is that exponent, the -5, your P of that value is going to be fairly close. So 10 to the -9th, this is about 9. 10 to the -10th, that's 10. 10 to the -4th, that's somewhere close to 4. So you can start to make some connections with what logarithms actually are telling you there. So I agree that this one, the strongest acid, is the one that has the most ability to produce H+ ions because it has a large Ka value. All right, if we just look now at a molecule like benzoic acid, and we're just to take a guess, what kind of a Ka value do we think this is going to have? Remember, we're thinking about that ratio. What does a Ka value tell us? Do we think it's going to be less than 1, equal to 1, or greater than 1? Let's do a couple more seconds. right. I'm gonna go ahead and close this out. Can I have a new voice describe what you chose and why? Maybe can I call on Nick?
So I chose A, but I'm honestly not really sure why I picked A. Is it because of the hydrogen inside of the benzoic acid?
So you're saying that because I bolded this hydrogen?
Yeah.
Okay, so it has to do with that. So having a COOH tells us that there's an acid. You'll also see that carboxylic acid is drawn out like this. Sometimes a COH, sometimes it's written as CO2H. Whenever we see that functional group in a molecule, we know that that is, regardless of what's attached over here, we know that that is going to act as an acidic proton. The question is, what does a Ka value of 1 or greater than 1 tell us? Can I get someone else to expand on why the majority of the class chose less than 1?
It's not a strong acid. That's why I picked A.
So what does it mean to be a strong acid?
Well, if it were a strong acid, then it would most of the benzoic acid molecules would dissociate. But since it's not, they won't.
Yeah, so if we're talking about, by the way, Amber, I just saw that you did the hand raise in the participants. Unfortunately, when I'm sharing my screen, I can't see all participants, so go ahead and just speak out. It'll be easier to do that way. If we're looking at the general equation of what Ka is telling us, we're talking about the concentration of our products over the concentration of reactants. And if we have a strong acid, that means we're going to have a lot produced on the right side. And so our general rule of thumb on this is if you have anything that is not considered a strong acid, which I'll show on the next page, then we assume it has a Ka value less than 1, meaning it doesn't have nearly as much generating the products. Most of it stays as a reactant, stays together. So let's actually come back to that question here in a second. So we're going to talk about strong electrolytes and strong acids, and I think it's kind of been brought up before. But the term strong electrolyte means that, like sodium chloride, when you put it in water, the sodium plus ions separate from the chloride minus ions. When we talk about strong acids, and actually it's not 100%, it's more like 95%, but close enough. Our strong acids, like hydrochloric acid, we make that same assumption. So what Jesse was referring to is this idea that if we put HCl in water, we don't really even have a Ka value because it's so far product driven, we can say it's 1,000,000 is going to be the Ka value, meaning most of the HCl, if we looked around and we found 1,000,000 HCl molecules, they're all going to be separate into H3O plus or H plus ions and chloride ions. They're not going to be together. And we describe that instead of using equilibrium arrow, we show this full headed arrow that points in one direction. Nitric acid is another strong acid, same thing. You don't see this equilibrium arrow. For chloric acid, sulfuric acid, all of these are strong acids, and all of these are going to need to be committed to memory. I don't say there's many things in this class you have to memorize. Polyatomic ions is one. That's a Gen Chem 1 thing that I think that everyone should have memorized. And the strong acids and bases are also things I need you to memorize. Am I missing any strong acids in this list?
Yes.
Which ones?
Hydrobromic acid, hydroiodic acid.
That's it. There's 6. There's only 6 strong acids you need to memorize. And what you need to know is we're not going to draw equilibrium arrows when we show those going into water. Those completely disassociate. They only form products. And that means that tells you something about how attracted these two things are to each other. So what I want you to think about, and I guess I'll make this a clicker question just so you have it on your own phones when I send you to breakout rooms. I want you to spend about 2 minutes in breakout rooms to try to discuss what does this mean about how attracted these two things are to each other. If they're strong acids, what does that mean about them being together, attracted to each other, or them being separate? And how does that differ from a weak acid? Okay, so I'm going to send this as a clicker question just so you have it on your screens. I don't care about your responses on clicker, but I'm going to send you into breakout rooms again. And I want you to try to figure out what kind of attraction there is between those two products and how we can justify that based on whether it's a strong or a weak acid. Breakout room should be open. All right, looks like we have a few people still chatting in the breakout rooms. Is that right? Yeah. Breakout rooms. That's hilarious. 2 of the rooms are still going at it, I guess, because no one from those 2 rooms has come. So interesting how this whole thing works. All right, here we go. All right, I'd like to hear from someone in Josh's breakout room. What discussion did you have about being a strong acid and the likelihood of it, how attracted those 2 things are to each other? Josh can nominate if he wants.
Jay, Nick, or Alexandria, you guys want to go, or do you want me to?
I don't know if I'm saying this correctly, but you kind of said like if it's a strong acid, it's pretty much happy with where it is. It's pretty stable, so it really won't be as attracted as opposed to, like you said, like a conjugate base who may be a little bit more unstable, who may want to reach out and grab it. And that's in the lamest terms possible.
I think that's a really good kind of way of describing it. So if we're talking about if this equilibrium lies really far to the right, that means that these 2 things right here must not be very well attracted to each other, the H plus and the Cl minus. If they were attracted to each other, they wouldn't let go in the first place. And when they did let go, they were so stable just being surrounded by water that they don't even want to come back together. There is no indication of the return arrow that exists for a strong acid. So what that tells you is that this Cl minus is a terrible base. It's actually so terrible of a base, meaning that it's not going to pull an H plus ion, that we don't even call it a base. It's like an insult to call it a base to any other base that exists, because they're like, it doesn't even want a proton. Why are we going to call it a base? On the other hand, if we talked about our weak acids, if you have like the ones we talked about before, where you have some sort of weak acid dissociating, and you get A minus and H plus ions. Aislinn, I'm going to mute you. Mute. Then you're going to have some on each side, but if you find much more of it on the left side of the equation, that means that these 2 things must have a really strong affinity for each other. Otherwise, you wouldn't have them coming back together. Basically, as soon as they separate, they're going to come back together or find another one and then go back to the reactant side. So the ones that are stronger bases, the worse of an acid it is, the stronger the conjugate base is. So I think I'm trying to look at where we are in our slides. Let's see which one of these. Let's do a really quick poll here. Actually, let's not do this quick poll. So we're gonna instead talk about the strength of this as a base versus this as a base. So earlier on, we talked about the fact that anything that accepts an H+ ion acts as a base. And in your homework, you had this description of Ka describing the reactions you've seen here. But then you also got introduced to this idea of Kb. And Kb is basically saying those things I've circled in purple, how likely are they to pull a proton off of water? How good are they at acting as bases? So it's almost the reverse reaction, right? It's saying that how likely is the reaction to go in this direction? But there's one major difference. And I'll show you based on the reaction we have here. So the reaction of Kb, I want you to look at what looks similar from the equation, basically this equation and this equation. What looks similar and what looks different from the reverse of this reaction to that reaction. Can anyone notice what's different between those two? Anyone see the difference?
What one of the product or one of the one of the products are?
Okay.
One of them has H3O and the other one has OH minus.
So we're looking at the reverse, just to make sure we're clear, of equation B and saying, is that the same as equation with a star? And so the difference is if we're looking at, I'm going to put something in a box, right? That's a reactant because we're saying the reverse here. But instead of having that react with hydronium, which it is in the products, it's reacting with water. And then the second thing is that it's generating OH minus instead of H2O. So the things that are the same are the things in the square boxes. But just like Ka is saying how likely is an acid to donate a proton to water, Kb is saying how likely is a base to pull a proton from water. So it's really important that on both sides that we notice Ka and Kb are both reacting with water. And you'll see why if we have time. It looks like we're at 7:12. The answer is we probably don't have time. Let me see if I can, I'm gonna move us forward a little bit here. And let's go to this slide here. So we're gonna do super quick questions. You ready? If we have neutral water, what do we say about the concentration of hydroxide and hydronium, H3O plus and OH minus? Concentration is equal, is one higher, is the other higher? Couple more seconds. Closing out. All right, what do we got? Ooh, 2/3 of the class think they're equal. I completely agree. In neutral water, the concentration of hydronium and hydroxide is the same. What is the concentration of H3O plus in neutral water? 10 seconds for this question. See how the questions are rolling in, the answers. So it's either 1 times 10 to the negative 14th or 1 times 10 to the negative 7th. I agree. Maybe let's ask this other question. what is the, maybe we can just have someone shout this out, or multiple people. What is the pH of neutral water? 7. Okay, we all know that, right? So when we have neutral water, we have pH equals 7, and that's because if pH equals 7, then the concentration of H plus ions, right, that's what the H stands for, is 10 to the negative 7. Right, so neutral water is this. So then that means that if we have neutral water, we have the same concentration of same concentration of H3O plus or H plus as we do of OH minus. What's the pOH of neutral water then? You can shout that out too. pOH of neutral water. Anyone?
7.
7. So basically, pH and pOH add up to always equal 14. And the reason for that is because of autoionization of water, which means if we have billions and billions and billions and billions of water molecules, and we were to go in and look, at any point in time, you're going to have 2 water molecules next to each other, and they do what's called autoionization. What that means is that you have one acts as an acid and one acts as a base. So this one acted as a base. It pulled a proton from this other water molecule. This one acted as an acid and donated it. And it's going to go back really quickly. And that happens all the time, but at really, really, really low concentration of water. So basically, if you looked around water, you'd see all these autoionizations happening, a really, really small amount. But because you started with water that wasn't autoionized, for every one OH minus, you're going to have one H3O plus. And so you have the same concentration of both. And the concentration is 1 times 10 to the negative 7th. So the idea that these concentrations are equal, and you define that by an equilibrium constant, that's kind of where we come up with this Kw equals 1 times 10 to the negative 14th. And more importantly than that, it's worth knowing that Ka times Kb is always going to equal 1 times 10 to the negative 14th. pKa plus pKb is always equal to 14. And also pH plus pOH is always equal to 14. So these equations are going to be useful for thinking about your primer for Wednesday's class. And we're going to spend some more time basically talking about conjugate acid base pairs in class on Wednesday. And I think that's pretty much all we have time for tonight. So starting in class on Wednesday, we'll start talking about conjugate acid base pairs and saying how something differing by 1 proton before and after, like we talked about earlier, is a conjugate acid base pair. If you have any questions or things you want to discuss with me, you can either stay on Zoom right now. I'm going to go ahead and stop sharing. Make that.
Is lab tonight over Zoom too?
Lab tonight is over Zoom to start, and then it's going to be a virtual lab. So Homindra will show you how to get started in your virtual lab over Zoom, and then he's going to be available for questions on Zoom.
Okay, for sure.
So I'll be here as long as you guys want and have questions tonight, and then I'm available by request any point in time. You can also use Blackboard discussions, but I really appreciate you guys sticking it out and showing up to class tonight. Hope you're all healthy and your families are as well.
Dr. Bailey, are we staying on this Zoom for Mr. Humindra's lab?
Nope, he sent you an email with a separate Zoom link.
Oh, okay.
Homindra's there. Homindra, it's the Zoom link you sent in an email, right?
Yeah, it's there. I just got it. Or like
Yes,
it's
Okay, cool. Thank you.
Okay. So he'll be
Is
available.
that it? Are we done?
We are done.
Okay, sorry.
Thank you.
No worries. Good to see you. Let me go ahead and stop the recording.